There we go, we're recording. So we've got a lot to get through today. I'm going to jump through some new categories of non-removable discontinuities that we haven't seen before. I guess sort of haven't seen before. I think they did show up on one of the study guides that I sent out, but I exited out saying you didn't need to know it yet. We'll look at evaluating whether piecewise functions are continuous or differentiable, which I do think we got to last year. We'll look at even versus odd functions, which is something that was way back from Algebra 2, but will crop up in the FRQs again. Some new theorems, and then factoring polynomials is something that, again, I think you guys did in Algebra 2, but it shows up again when trying to find zeros later, so we'll take another look today. Okay, so this is from our cheat sheet for the final exam last year. We've got continuous, removable, and non-removable discontinuities were all you guys needed to know last year, but we can split non-removable discontinuities into 3 new categories that I don't think we've seen yet. So those 3 new categories are infinite, jump, and essential discontinuities. An infinite discontinuity is like a vertical asymptote. So it's any time when any of your one-sided limits are approaching positive or negative infinity. Your jump discontinuity is whenever you have different y values from the left than you do from the right. And essential is anytime you have a dead end, or at least one of the one-sided limits does not exist. I've drawn a dead end here. It is possible to have an essential discontinuity if you had something like maybe the sine of 1 over x. So if I had the sine of 1 over x, as you get closer and closer and closer to x equals 0, this number in the inside part of the sine function should get bigger and bigger and bigger, right? So if you're dividing by a really small number, then your answer gets bigger and bigger and bigger. And if my sine of my angle is the sine of a number that keeps getting bigger, then it will keep bouncing between 1 and negative 1. So if I go to graph this, something really weird happens, in that no matter how close you get to 0, we keep bouncing forever between 1 and negative 1. So there's no one number that we approach on either side. So that's also an essential discontinuity. It's a very rare type of essential discontinuity that I would call an oscillating function. But it's an essential discontinuity still because, in this case, both of the one-sided limits do not exist. Both from the left and the right as we approach x equals 0. We don't have a set y value that we get close to. It just keeps bouncing between 1 and negative 1 forever. Okay, then we talked briefly about differentiability last year. In order for a function to be differentiable, it must be continuous, and we have to approach the same slope of that function from the left and from the right. So an example of a function that would be continuous but not differentiable would be some sort of a cusp. So in this case, as I approach x equals 3 from the left, my slope is positive, and kind of a sharp positive slope. But as soon as you pass x equals 3, my slope jumps and changes to a negative slope. So in this case, I'm not differentiable because our slope is not approaching the same value. Normally, you'll have a smooth curve where your slope does approach 0 from the left. I'm getting closer and closer to a slope of 0. And from the right, I'm also getting closer to a slope of 0 as we get close to this point. So in that case, I would be differentiable because we are continuous. I do have a general limit. We're approaching the same y value. When I plug it in, I get the same y value, so we are continuous. And our slope is both approaching 0 from the left and from the right. So in that case, I would be differentiable. So if I wanted to make a flowchart, it would look like this. If our function has a general limit, then we could be continuous, or we could be removable discontinuity. If we are continuous, then we could be differentiable, or we could be non-differentiable. So what that means is, if you are told that your function is differentiable, then you already know that your function is also continuous, and that your function has a general limit. All functions that are differentiable are continuous. All functions that are continuous have general limits, but it doesn't work backwards. Not all functions that have general limits are continuous, and not all continuous functions are differentiable. Okay. And then if our function does not have a general limit, then we put it in this big category of non-removable functions, which can still show up in the AP exam for your multiple choice answers. But usually on the free response, they may want you to be more specific than that. And if they want you to be more specific than that, then we can break non-removable discontinuities down into infinite jumper essential. Okay, so let's try a couple. I'll do the first one, and then I'll have you jump through a couple of these others. So for the first one, my limit as I approach x equals 1 from the left is -1. My limit as I approach x equals 1 from the right, so coming in from the right, is also -1. That means my general limit is -1 because I have the same limit from the left and the right. From the left, I was approaching a y value of -1. From the right, I was also approaching a y value of -1. If I plug it in, I also get -1 because it's a filled-in circle there. If it's not a filled-in circle, then I'll go somewhere else. So my continuity is continuous. Okay, what's happening at x equals 2? Perfect. Removable. Okay, so we can say jump now and be as specific as possible. Okay, how about 4? Okay. I'm gonna write these out for now because they're new. When we actually go to test on this, I'll have a key that says you can write I or J or E or R or C for all of these, but okay. X equals 5. Perfect. And 6. Perfect. 7. Yeah. Also essential. Okay, I'm gonna write E for now. Perfect. All -2 and continuous. And 9. Do any last one? Yeah, hiding in the bottom now. Jump. Perfect. And last one, 10. Infinite. Perfect. Okay. If I wanted to distinguish between a removable discontinuity and an infinite discontinuity, and I gave you a function instead of a graph, the removable discontinuities should cancel out. So that means for a rational function, what gives you a 0 on bottom should be the same thing as what gives you the 0 on top of your fraction, if it's removable. If it doesn't cancel out and it gives you a 0 on the bottom of your fraction, then it's infinite discontinuity. So in this case, If I factor the top, I would have x times x minus 3. And then on bottom, I still have x minus 3. So at x equals 3, I am still discontinuous for my original function, but I could cancel out that discontinuity in order to get rid of or remove that problem. So this is a removable discontinuity. Removable discontinuity at x equals 3. However, for this function, I'm already factored and I can't cancel anything. So at x equals 7, I have an infinite discontinuity. I could also say at x equals 7, we have a vertical asymptote. Oh. Correct my English here. There is a okay. So that means if I was going to graph this, my graph would look like y equals x for this one, which is just a straight line, passing through 0. There we go. But when I got to x equals 3, I would have a hole. Okay, and then if I was going to graph this one, then at x equals positive 7, I would have a vertical asymptote. So my graph might look something like this. Let's see, I've got a horizontal asymptote actually at y equals 1. So I'm going to get really close to these two lines, which I know because if I plug in 0, I'm at negative 3/7. So I'm going to get really close to those two lines. Actually, a little bit lower. There we go. And then if I pass x equals 7, so I plug in 10, then I end up with 13 over 3, which is going to be more than my horizontal asymptote of 1, so my graph will look something like that. Okay. If I wanted to know whether this function was continuous, differentiable, both, or neither, what would I have to do? What has to be true if our function is continuous? Yes. What must be true if our function is continuous? Okay, so the general limit has to be the same as what happens when you plug it in. That's an even better answer than what I was going to write, but in order to check for my general limit, I would check from the left and the right. And then if all of that is true, then the limit as x approaches 3 of f of x in general should be equal to f of 3. So if all of this is true, then we are continuous. Okay, so what do I need to do to check and see if the limit from the left is the same as the limit from the right? Let me ask this a different way. What is the limit as x approaches 3 from the left of f of x right now? $11, perfect. How did you do that for everybody else who's listening? Okay, why'd you pick the first function? Perfect. So if I'm looking for the limit as x approaches 3 from the left, then we should be a little bit less than 3, infinitely less than 3, but that still means we're less than 3, so I've got to use this top function. So that gave us 11. Okay, what about the limit from the right? Also 11. Okay, and that's the same thing as what happens when we're equal, so this second part is also true. So what does that tell us? Not differentiable yet, we haven't proven that. Okay, we know it's continuous. Okay, so we could say the limit as x approaches 3 of our function is equal to f of 3, therefore f of x is continuous at 3. X equals 3. If you want to shorthand therefore, you can do this triple dot thing. It looks like the Terminator, but therefore f of x is continuous at x equals 3. Okay, and then we also need to prove whether or not it's differentiable. So how do what additional step do I need to do to prove it's differentiable? Limit from the left of what, though? That's what we did up here, actually. So that's what we did to check for continuity. We're checking differentiability, so we're really talking about the slope. So I'm going to check the limit as x approaches 3 from the left of the derivative. So I want to know, is the limit as x approaches 3 from the left of the derivative equal to the limit as x approaches 3 from the right of the derivative? And if that's true, and we are continuous, then we're also differentiable. Okay, so I need to derive both of these. So what would my derivative look like? Okay, so as long as x is less than 3, my derivative is 2x. And how about the bottom? 6, as long as x is greater than or equal to 3. So if I plug in 3, what's going to happen? It's equal. Okay, so what does that tell us? Okay, so therefore f of x is also differentiable. Okay, so if you're testing for differentiability, we do need to go through all of those steps. However, if any one of those steps is not true, then it's automatically not differentiable, because if we're not continuous, it can't be differentiable, and if it doesn't have a general limit, it can't be continuous. Okay, so in this case, we are C, both continuous and differentiable. I'm gonna let you try one more on your own. Okay, so let's start with, we're going to start with our general limit and see if we can prove that this is continuous. So what do I have to do first? Okay, so if we check the left side, what happens? Sine pi over 2, okay, is 1, perfect. And then what about the right side? Okay, what's the cosine at pi? -1. So I've got -1, and that is the same. So that means there is a general limit. And in this case, because that last part was also equals, we are continuous. Okay, so f of x is continuous at x equals pi. Okay, and then I've got one more thing I need to check for differentiability. Perfect. Okay, cool. What's the derivative of the limit from the left? Chain rule. With chain rule, you need to multiply by the derivative of the inside part of your function. Okay, so if derivative of sine is cosine, then we can look at the inside part of our function. What's the derivative of the inside part of our function? Okay, my inside part is this x over 2. So that's the same thing as 1/2 times x. What would happen if I derive that? One half. Okay. And then what happens if I derive the right side? Okay, so it's positive sign, because that was really negative sign. So this is sine of x multiplied by 1. So I don't need to write it, but you're right. This will be multiplied by 1. Okay, then I need to plug in pi into both of those, and we're good to go. Okay, 0, and the sine of pi? 0. Okay, so what did we just prove? Perfect. All right, I think you got it. Any questions on continuity before we move to the next thing? All right, moving super fast. Oh, sorry, I've got one more. Okay, if we're not continuous, is it possible for it to be differentiable? No. All functions that are differentiable are continuous. So if we're not continuous, we can stop. Alright, so that means this one's neither continuous nor differentiable. Okay, that's the reason why I want you to work in this order, is because it gives you the least amount of work if something fails. Okay. So I'm back to a couple old algebra stuff that I'll go through really quickly, just because it pops up on some of the free response later for homework. If we have an even function or an odd function, an even function is if you can plug in negative x instead of plugging in x, and still get the same y value, then your function is even. The way I think about it is if I was going to take my whole piece of paper and fold along the y-axis, so just fold that whole function in half about x equals 0, would I end up overlapping myself? So if I took this, change my color really quick because this is already red. If I took this half of the paper here and then folded this half onto this side, then they would overlap, right? Okay, if that's true, your function is even. Okay, versus an odd function is your y value is the same if I plug in negative x as if I took the negative of the entire original y value. So if you multiplied the original y value by -1. The way I like to think about this is if I had two people that were looking at the same graph from different sides of a desk. So what this person saw and what this person saw would be the same if our function was odd. So if you could flip your piece of paper 180 degrees and have it look like exactly the same function, then your function is odd. So in this case, I'm just taking this exact drawing and flipped it 180 degrees, which is why you can see all of my writing is upside down. But if you turn it 180 degrees, you end up with a picture that looks the same, which is true for y equals x cubed. And it's also true for y equals the sine of x. So here's my sine function. If I keep going for the other side, it would look like this, right? So if I take that function, and we flip that picture 180 degrees. So here's our sine function. And I'm just going to spin this 180 degrees. And if I do, you can see it's still a sine function. Okay, as long as that's true, we have an odd function. All right, but if you want to test for it without a graph, then you'd have to use this equation. So what we're really doing is I'm changing my input to be negative. So if my negative version of my input equals my negative version of my output for the original function, then we're odd. For an even function, if the negative version of your input equals the positive version of your input, then we're even. All right, any questions on even versus odd functions? Okay, it's really just a vocabulary thing. It does show up as one step of one of the free response questions for the homework. But I wanted to go over it because we didn't talk about it at all last year. Okay, more new stuff. I've got two really easy theorems and then a third hard theorem. So easy stuff first. The extreme value theorem says as long as our function is continuous on some sort of an interval, so we're continuous from x equals a to x equals b, then there will be at least one maximum and at least one minimum. Now from last year, we learned that we could have relative minimums and relative maximums. So for instance, this function here at, oh, let me make a start point and end point too. A, B, C, D, E, F, and G. Keep going for one more. H, I. Okay, so I've got this function from A to I. I have relative maximums at B, D, F, and H, because compared to the points around them, they are high points. I could also say the slope is 0, but we changed from a positive slope to a negative slope at B, D, F, H. So those are relative maximums. At C, E, G, we have relative minimums, because our slope is 0, and we changed from decreasing to increasing at all of those points. If you wanted to do a first and second derivative test to prove it, then any relative maximum will have a slope of 0 and be concave down, which means your second derivative would be negative. Concave down looks like this. Concave up looks like this. So this is your second derivative is below 0, and this is your second derivative is above 0. So we can use that to test for relative minimums or maximums as well if you don't have enough information to test to see what's happening to your slope around that point, which could happen on the AP exam if they gave you a graph. So a lot of times you'll end up with something like this, where they'll tell you these are your x values, your y values, your derivative, and your second derivative. So they'll tell you your first derivative is 0 for this first point. Your second derivative is -1, your y value is 3, and your x value is 1. They'll say, is this point at x equals 1 a relative minimum, a relative maximum, or neither? What would you say? Okay, so in this case, we've got a relative maximum. I've got a relative maximum because my slope is 0, so that means we know we have a relative minimum or a maximum, but we're concave down. So if I have to have a slope of 0, but we also have to be concave down, then my graph should look like this at that point. So I would have to have a relative maximum. Okay, cool. Versus if this number had been positive instead. Relative minimum, perfect. Okay, that's a very tricky way of asking for relative minimums or maximums. You don't know anything about the points around it, but it's possible to ask you in a table. And in that case, you would need to know, you would need to compare the first derivative to the second derivative in order to figure out whether it's relative maximum or minimum. In this case, we're looking for not relative minimums or maximums, but absolute minimums or maximums. So that means the tallest y point and the shortest y point. So what's the highest value and what's the smallest value? So in this case, what's my highest value of this red function we just drew? Yep. F. And what's the lowest value? I. Okay, so it is possible for an absolute maximum or minimum to be the start point or end point of a function. Or an absolute minimum or maximum could be any of your critical points. Those are points where your slope is 0, which are your relative minimums or maximums. But that does mean we need to test the start point and end point if I'm looking for an absolute minimum or maximum. Okay, all we're looking at today is as long as we know that your function is continuous from a to I, then it must have at least one high point and low point. Even if your function is a straight line, in that case, every point is the high point and every point is the low point, and this is still true. If our function is not continuous, though, so if we have a jump discontinuity, for instance, then we don't know for sure. Okay, so for instance, we've got our function defined from an interval, start point A to end point B. Let me go over interval notation really quick, because I haven't done that in a while either. If you see an open notation like this, that means A is included and B is also included. A and B are okay. Versus if I use parentheses instead, that would mean the endpoints are not okay to plug into the function. A and B are not okay. Okay, so in this case, our interval starts at A and goes to B, and it's okay to plug in A, and it's okay to plug in B. We can also mix these notations. So if I wanted it to be okay to plug in A, but not okay to plug in B, we can do that. Okay, it's okay to plug in A and B, our start points A, endpoints B. Also, our Y values are the same if I plug in A, C, and B, where C is some number between A and B. If our function is continuous, which of these have to be true? Sure, okay. What do we know so far? Okay, so we've got solid points at A and B. What else do we know about A and B? Okay, so we were told that f of A equals f of C equals f of B. So that means the y values of all of those points are all the same. B. Okay, what else were we told? Function is continuous. Okay, f of x is continuous. So if f of x is continuous, which of these should be true? Not sure. I'm going to draw a bunch of different examples and just make this as weird as possible. So I have to be continuous. So I'm going to draw a function that's continuous but not differentiable here, because why not? And then I'll bounce around a little bit between these just to kind of play with it a little bit. Okay, so right now I was continuous. Here's another option. So I just have to pass through 3 points that have the same y value. I could have done this and just been the same y value throughout. I could have gone up and down through all 3 of those points. Okay, so here's a bunch of counter examples. Did I have a maximum or a minimum for this first one? What about the second one? Okay, and the third one? What do you think the right answer is? D, okay. So we have both a minimum. Oh, I see. I accidentally left my n over there. No wonder I'm confusing you. Okay, so we have both a minimum or a maximum is what that should read. So that should be and, really. Oops. Okay, I blew that with my English, but we have both a minimum and a maximum. Which is true as long as our function is continuous, according to the extreme value theorem. Usually this is going to come up not in the multiple choice, but in the free response, where they will ask you to prove why this function has to have a maximum value in some sort of a real-world context. So maybe your free response question is talking about a machine that tracks how much gas passes through a pipe. That way the company knows how much gas is used. Your derivative would tell you how fast the gas is passing through the pipe, and your second derivative would tell you the acceleration. So they would ask you, as long as gas is flowing continuously through this pipe, how do you know that there is maximum or minimum amount of gas that we end up in this barrel at the end of the pipe? And you could say, we know there's a maximum or a minimum because of the extreme value theorem. As long as our function is continuous, there has to be a maximum or a minimum. Okay, intermediate value theorem. The intermediate value theorem says as long as our function is continuous on AB again, there should be some value n such that the y value passes through n as long as n is between f of a and b. Okay, what that means is as long as our function is continuous, we have to pass through all the y values between f of a and f of b. Again, the way they're going to ask about this is usually in your free response. And a lot of times it'll be about the derivative. So in the case of our gas example, you could say that the rate at which gas was flowing in the pipe, so I'm going to call this G for gas prime, at 3 minutes was 40 liters per second. And the rate at 5 minutes was 100 liters per second after we started ramping up the speed. And I would ask you, was there a point at which the gas was flowing through the pipe at 50 liters per second? And you would tell me, yes, there has to be at least some time between second number 3 and second number 5 where the gas was flowing at 50 liters per second because of the intermediate value theorem. I know for our derivative that we were flowing at 40 liters per second and eventually started flowing at 100 liters per second. So even though I don't know anything about the function in between, liters per, second number and liters per second, really. So this is G prime that I'm graphing, and this is T, measured in seconds. Okay, because I know that we were 40 liters per second here and 100 liters per second here, there must be some time, probably a crazy decimal between 3 and 5, where our gas was flowing at a rate of 50 liters per second. There's also a time where our gas is flowing at a rate of 90 liters per second. What we can't prove is that there was a time where we were flowing at 30 liters per second, so that's below our starting value, or 110 liters per second above. It is possible, but we can't prove it. Don't have enough information yet. Okay, so here's 2 more examples taken from multiple choice questions. From top one's BC, bottom one's AB, but you're required to know everything on AB as well, so it still works. Okay, so I've got a function that is continuous from -3 to 6. f of negative 3 is negative 1, and f of 6 is 3. The intermediate value theorem guarantees that one of these is true. I'll let you read through, and then, well, actually, let's read through together, and you'll tell me true or false for each of these, I guess. Okay, f of 0 is 0. Does that have to be true? Maybe, okay. Okay, it could be true, but it doesn't have to be. The derivative is 4 over 9, at least once between x equals negative 3 and x equals 6. So does it have to be true, or does it not have to be true? Okay, so this one doesn't have to be true, but let's talk about what we actually know so far. So we know f of negative 3 is negative 1, so I'm just going to draw a graph really quick. I know f at negative 3, negative 1, 2, 3 is negative 1. And I know f at 6, 1, 2, 3, 4, 5, 6 is 3. Okay, all we know is that these 2 points exist. We also know the function is continuous, so I can't have any crazy breaks in the function. Okay, we were also given a big hint here. So we know what theorem we have to use to prove this is true. Okay, so intermediate value theorem doesn't say anything about the slope. Also, anything could happen here. So we don't necessarily have to have any slope. So this one doesn't have to be true. I'm going to write maybe again. F of 0 is 0. Again, we can get from point A to point B however you want to draw this. So I don't have to pass through this point specifically. So that one's maybe true, but not guaranteed. Okay, how about C? Okay, so it says our y value has to be between negative 1, which is this point, and 3 for all x values between x equals negative 3 and x equals positive 6. Okay, does that have to be true? No. We could go down. Okay, so that doesn't have to be true. So, maybe. Okay, our y value equals 1 at least once between negative 3 and 6. Okay, that one does have to be true. Guaranteed, which is what we were looking for. Because we started at x equals negative 3 and went to 6, and I have to pass through every y value at least once. We could go down, we could go up and down, but we have to pass through that y value of x, or y equals 1 at least once. Okay, what about E though? The y value has to be 0 between x equals negative 1 and 3. Maybe. Okay, why is that maybe and not guaranteed? Perfect, it's not the start point and the end point. So we could have passed 0 way over here before we even got to negative 2 and then went over. Okay, a lot of times what I try to do with these, if I'm not sure, is I try to come up with a couple examples. And if I can think of what's called a counterexample, so example where this is not true, then I know that that answer is wrong. So if I was completely lost on this one, I would draw a couple crazy ways that I could get from A to B. So straight line, or go down and up, or go up and over. So a couple of these, and just check to see if that's still true. And that would usually get me to at least a 50-50. Okay, one more. F is a function that is differentiable from 1 to 10. F of 2 is -5. F of 5 is 5. And f of 9 is -5. So I've got something like this, 3 points that we know about. If we are differentiable, it could be. Doesn't have to be, but it could be. Again, it could be something like this. Okay. We actually cannot be this because we know we're differentiable, so we do have to have a smooth curve. But that doesn't have to be the top point either, so I could be something like this instead. And that would be okay. Alright, but if I am differentiable, they did just tell us a lot of information actually, because in order to be differentiable, what do we also have to be? Yes. Okay, so we know that we're differentiable, and we know that we're continuous, and we know that all three of these points exist. These two are at y equals -5, and these ones are at y equals +5. Okay, so the first one says f has at least 2 zeros. A zero is whenever you touch the x-axis. Okay, that is true. In order to get from point A to point B and to point C, I have to pass at least twice. It is possible to do more than that. In fact, you could pass infinitely many times and still be okay. But there does have to be at least 2 zeros. Okay, the graph of f has at least one horizontal tangent. Horizontal means a line that goes left and right. Tangent means a line that touches your function. So in this case, we will have a horizontal tangent line as long as our slope is 0 at one point. So, okay, sure, that's true. In order for me to curve back, if I am differentiable, that means we can't have a cusp. Then I have to have a point where the slope was 0 in order to curve back. So that means there will be at least one horizontal tangent. Again, we could have infinitely many of them, but we have to have one. Okay, and the last one. For some c, so that's some x value between 2 and 5, and that is our start point and our middle point. Our y value has to be equal to 3. Yes, true. Why is that true? Okay, we need to pass through all the y values. If they ask you on a free response, you should say because of the intermediate value theorem. Okay, so all three of these are true. That means E is correct. Okay, I'll circle this one over here for everybody else. So D and E if you're waiting until the end. All right, any questions on 1 or 2? All right, so I promised you 2 easy theorems and 1 hard one, so I've got 1 hard theorem left. So the mean value theorem says if we are differentiable, this is different because all of the other theorems required us to only be continuous. If we are differentiable, then there is at least one point C between A and B, such that the derivative at C, so the slope at that point, is equal to your average slope between A and B, your average slope between your start point and end point. If I was going to draw a picture, it would look like this. So I've got A, C, and B here. If I was going to draw a line, that line would have a slope of your average slope equation from algebra. There should be some derivative between A and B, at least one, where the slope at that point, which would be the instantaneous slope or the derivative, will be equal to your average slope. That's the mean value theorem. Another way of saying this is that the slope of a secant line from A to B must equal the slope of a tangent line for at least one x equals c on our interval a to b. Okay, this I can actually make these parentheses because it can't be the same value. Okay, which looks like this. It's actually the same picture if you notice. My tangent line just means the line that touches our curve. And what we're really doing when we find a derivative is we're finding the slope of a tangent line. We are taking the limit as x approaches c of our average slope between 2 points. So this is one way of saying our derivative. Is I've got 2 points, x and c, and if I squish them into 1 point so that x becomes c, and take the slope at that point, then I would get the derivative. Okay, another way we learned last year was the limit as h approaches 0 of f of x plus h minus f of x over h is also equal to the derivative of x. I think my video just cut off that side there, so I was trying to squeeze that in, but that's f prime x on the right side. So this one is talking about the really your change in x instead. So this is saying if your change in x from 1 point to the next becomes 0, then you're not changing your x anymore, and you'll only have 1 point. And if we take the slope, you'll get your slope at 1 point. So the idea is the same. It's just different ways of writing it. This one we call the formal definition of a derivative. This one's the limit definition of a derivative. They're both really the same thing. Anyways, the slope of a tangent line is just a line that touches your curve at 1 point, is your derivative. Slope of a tangent line is the derivative. And AP loves to ask about derivatives instead of asking about derivatives directly, asking about the slope of a tangent line, just because that adds a layer of difficulty to it. So it doesn't make the question any harder at all. They're just testing to see whether you know that the slope of your tangent line is really the same. They'll also sometimes throw either of these formulas out in multiple choice, when really all you have to do is derive the function that they gave you. Testing to see if you know that this is a derivative and this is a derivative. I believe I gave you this originally last year as a change in x instead of an h. These variables could be anything, they just tend to be written as h on your AP exam. If you see h on your AP exam, a lot of times they'll use h for step size, which is a change in x. But really they can pick any variable they want. It doesn't have to be h. They can pick any letter. Okay, so how do we use this? Well, if I just wanted to ask you what x value would satisfy the mean value theorem, so that's, I'm going to give you a function in an interval. So here's x equals 2 and x equals 5. And I want to know what value satisfies the mean value theorem, then using my picture, what I'm really asking you for is this. I'm going to break out so I can get a ruler really quick. Ruler. Oh, come on. Oh, I think I did too much at once, so there we go. Okay. So something like this. I've got a line that touches those 2 points, and there should be a line at some point in between them that has the exact same slope. I want to know what the x value of that point is. Okay, so what we're going to do in order to find it is we're going to find out what the average slope is between our start point and end point first. So that means my first step is going to be to figure out what the y values are so that we can use our slope equation, change in y over change in x, to figure out the average slope. So I'm going to plug in our start point into our function. If I do plug in 2, I'll get 4 over 2 minus 4 minus 3. So that's 2 minus 4 minus 3 is negative 5. If I plug in 5, I've got 25 over 2 minus 10 minus 3, which I'm going to make everything over 2, so I've got common denominators, and I get negative 1/2. Okay, then I can go and get my average slope. That's change in y over change in x. So here's y2, negative 1/2, minus y1, negative 5, over x2, 5, minus x1. Again, you can change the order, but it has to be the same order for the numerator as you use in the denominator. So if you want to do x1 minus x2 on the bottom, then you have to do y1 minus y2 on top. Okay, you'll get the same answer, but my average slope ends up being, I've got 9/2 over 3, so that's 9/6. 9/2 over 3 is the same thing as 9/2 times 1/3, means 2 times 3 is 6 on bottom. You can cancel 2 3/2. So I've got my average slope. The mean value theorem says my derivative should be equal to the average slope at some x value. So what I'm going to do is I'm going to derive our original equation to get f prime, and I'll set our average slope equal to that derivative, and then we can solve for x, and that will tell me what x value gives us a slope that's the same as our average slope. Okay, so to derive our function, if I derive our function here, I would get 2x times 1/2 minus 2. Okay, so my 2 and the 2 can cancel, so that's x minus 2. Okay, 2 is the same thing as 4 over 2. If I add that to the other side, I get 7/2. So at x equals 7 over 2, my derivative is the same as my average slope. And I can check, because this x value should be between our start point and end point in order to satisfy the mean value theorem. 7/2 is 3.5, which is between 2 and 5, so we should be okay. All right. Any questions on mean value theorem? Maybe later, okay? Last thing for today, I've got 20 minutes left. is I want to go back through finding the zeros of a polynomial. So this is factoring polynomials. I believe everyone is really good at factoring quadratics. So that's when you have a power of 2. I don't think anyone had any trouble with that in our class last year, but if I'm factoring something that is not a power of 2, so something to the power of 7, then it's been at least 1 year since you guys saw that in this class, I think. So I know we didn't do that last year for pre-calc. At least I don't think we did. We might have at the very beginning of the year. Anyways, so if I wanted to factor a polynomial that is not just a quadratic, then what we'll end up doing is we'll find the possible zeros, which I'll explain in a second. Once you know all of the possible zeros, we can start testing them with synthetic division. Synthetic division divides out one zero from a number of other zeros, and leaves you with a polynomial that is 1 degree less than what you started with. So for synthetic division, this would be, take a step back, this is 4x cubed plus 3x squared plus 0x plus 4 in this case, which I haven't actually tested to see if this is going to work, but if I wanted to test whether x minus 1 is a factor of that polynomial, so that means x equals 1 would be a 0, I can write all of my coefficients here on top, so that's 4, 3, 0, 4. I do have to include a 0 if that term's not shown. And the 0 that I'm guessing for. Then we add down, so 4 plus 0 is 4, and multiply across. 1 times 4 is 4. Add down, 7, multiply across. 7 times 1 is 7. Add down, 7, multiply across. 7 times 1 is 7. Add down, 11. Okay, if I get a remainder, so in this case I did get a remainder, then this is not a factor. Okay, so because I don't want to start testing this problem for every possible number, I am going to show you a trick to get a number of possible zeros that will limit the number of stuff you have to test. Ideally, we would get a remainder of 0. So I'm going to change our problem so that we force ourselves to get a remainder of 0. So if this last number had been a negative 7 instead, then in that case, I would have added down to get 7, multiplied across to get positive 7, and then ended up with 0 for my remainder. So that tells me this is a factor, x minus 1 is a factor. And what I'm left with is 4x to the 1 power less, so that's 4x squared, plus 7x plus 7. And I could keep going from there because now we're a quadratic. Unfortunately, I was just picking this number at random, and this one doesn't factor evenly, but we would know at least 1 0 here, and my last 2 zeros in this case would be imaginary. Okay, so I'm just going to keep repeating synthetic division until we get down to a quadratic, and then we can factor using all of your rules from algebra once we already have a quadratic. And then at the very end, we'll go back and we'll list all of the zeros that worked, and we can write our original polynomial in factored form if we need to. I believe for the homework, you're just looking for zeros for part of your APFRQ. So in that case, your 0 would be 1, and that's your only 0 for this polynomial. Okay, so I'm going to go through a whole example and also explain what's going on here. So I've got 2 theorems I'm going to use. The first one is called our complex zero theorem. This ended up a lot smaller than I thought it was when I first wrote this. Can you still read, or is that too small? It's okay, all right. So the complex zero theorem, which you don't need to know the name for. Unlike the other 3 theorems we learned today, you do need to know the name for the AP exam. This one, as long as you can use it, they will never ask you the name. Complex zero theorem tells us that the number of changes in sign of your function relates to the number of possible positive zeros. So if there were 7 changes in the sign, then I could have 7 positive zeros, or 5, or, oops, sorry. or 3 or 1. It always goes down by 2 at a time. And the reason why it always goes down by 2 at a time is because it's possible to have imaginary zeros. So if I had a function that was curving a lot, so something like this, normally for every curve, every one curve that I have, you get 2 zeros, right? Okay, but if we had a curve that did not give us a 0, we never reached 0, then we actually lost 2 zeros from not reaching 0, not just 1. Those 2 zeros would end up being imaginary. Okay, so that's why these are always going down by 2s. Okay, so for my example down here, I have 4x cubed minus 3x minus 1. That's a positive, negative, negative sign. So I changed signs once, and then never changed again. So that tells me there is one possible positive 0. Okay, but our complex zero theorem also tells us a way that we can get the possible negative zeros, and that's by changing our input to a negative x. And if I did that in this case, so I'm going to plug in negative x in here, then my function of negative x would be 4 times negative x cubed minus 3 times negative x minus 1. And that only changes our odd powers signs. So I've got the final answer down here if I simplify. This becomes a negative 4x cubed and a positive 3x, right? So now I've got negative, positive, negative for my signs, and I change 1 2 times. There are 2 or 0 possible negative zeros in this case. Okay, so for possible positive zeros, we test with f of x and just count the changes in sign. For possible negative zeros, we test with f of negative x and count the changes in sign. For both cases, it can either be that number of zeros that are true when you factor, or go down by 2s. So if you ended up with 4 changes in sign, you could have 4, 2, or 0 of those zeros. Okay. And then in order to figure out which numbers to test, so this tells us it might be better to start testing negatives because there are 2 possible options instead of just 1. But then in order to figure out which numbers we actually want to use synthetic division for, our rational zero theorem says the numbers that are possible zeros will always be factors of your constant, so that's the last number, divided by factors of your lead coefficient, so that's the first number. So a coefficient is a number that's in front of your variable. So in this case, our leading coefficient is 4. Constant is a number that does not have a variable, so in this case, our constant is -1. However, these factors can be positive or negative because we're multiplying. In order to get -1, I could multiply +1 times -1. In order to get 4, I could multiply 2 times 2, or I could multiply -2 times -2. So all of these are going to be positive or negative options. Okay, so I've got factors of my constant, -1, are only plus or minus 1. But the factors of my lead coefficient, 4, are 1, 2, or 4. 1, 2, or 4. So any combination of these numbers that we can make is a possible 0 that we could test with synthetic division. Which sounds like a lot of work at first, but we've actually really limited our options from being infinitely many options that we would have to test to now only 6. And we know of those 6, if we find one possible positive 0, then there won't be any more left. So we actually shortened our amount of work we have to do significantly. So all combinations of these are okay. So I could do 1 and positive 1 or 1 and negative 1 would give me plus or minus 1 over 1. Or I could do 1 over 2, again plus or minus 1 over 2. Or I could do 1 over 4. If I had had a different constant, so if that had been 2 instead, then I would have 1, 2, and I would need all combinations of 1 over 1, 1 over 2, 1 over 4, and 2 over 1, 2 over 2, 2 over 4. That's 12 options. But again, that's 12 options to test with synthetic division, and then once we get down to quadratic, we're really not testing anymore, we're just factoring normally. So it's not as much work as it seems. Also, College Board knows you're on a time limit, so if you ever have to do one of these, you won't end up with too many factors. Okay, so to keep going with this example, so I'm going to copy this whole slide over to the next one, so you can still see all our work from last time. Here's all of our zeros that we had, and we said there's 1 possible positive and 2 possible negative. Okay, so I started out saying that 1 is the easiest to try with synthetic division right now because I don't want to worry about fractions. And I started trying the negative 1 first because I'm already 3rd power, and if I find 1, I'll be 2nd power and factor. And we know there's more negatives than positives, so I figured negative 1 is more likely. So I'm going to write all of my coefficients down here for synthetic divisions. This is 4x cubed, so 4. 0, x squared, so 0, negative 3, x first, so negative 3, and negative 1, x 0 is negative 1. We always add down, so that's 4 plus 0 is 4, adding down, and then multiply across. Negative 1 times 4 is negative 4. Add down, negative 4, multiply across. Positive 4, add down, positive 1, multiply across. Negative 1, add down, negative 1 plus negative 1 is negative 2. And we have a remainder. So negative 1 is not a 0. Now the cool thing about this is negative 1 is not going to be a 0 for the entire rest of this testing. So even if we were x to the 7th power, and we got synthetic division and got a new polynomial for x to the 6th power, we don't need to test negative 1 again. So we know negative 1 is not it. Okay, I had an option of keep testing with negative 1/2, which might have been a better option if I didn't care about fractions, because there are 2 negative zeros instead of just 1. I chose to go ahead and do 1 because it's fast and there's not a fraction involved. So if I do 1, this is add 4 down, multiply across is 4, add down, multiply across is 4, add down, we've got 1, multiply across is 1, negative 1 plus 1 is 0. That worked. So x equals 1 is 0, and that means if I wanted to factor this, if x equals 1 is 0, then x minus 1 is my factor. So I'm left with my factor of x minus 1, and the polynomial I was left with the remainder of 0. So this is 4x squared plus 4x plus 1 is the same thing as f of x. I've just factored 1 out. Okay, so all I've done is I've moved my work over to the left so I have more room to work on the right side here, because now I'm left with 4x squared plus 4x plus 1, which we can factor normally with algebra. So that gives me, if I factor this, 2x plus 1 and 2x plus 1. So I actually ended up with 2 zeros that are x equals negative 1/2, and 1 positive 0, which is exactly what we predicted. Okay, we are right on time, so we got 5 minutes left, so we're 5 minutes early. Any questions on anything that we did today? Okay, that was a lot. I wasn't sure if we were going to finish on time, but you were super fast. I'm going to go ahead and post all of our annotated PowerPoints to the WeChat group. And the homework's also up on WeChat right now, which I'm also going to post to course sites later with the submission link. Post a course sites submission link later this weekend, along with YouTube and Chinese video host links. Next week is mandatory, so please join us at 8 p.m. Saturday, August 8th. Yeah. All right, thank you so much for coming. This would have been really awkward if I had to pretend there was a class room and there wasn't. And I'll see you next week. Let me know if you got any questions in WeChat, okay? Goodbye.